Hello. Yeah, I want to start out by saying that I appreciate you all coming to this talk today. With a talk title like this, you know that it's going to be filled with like dry historical misrememberings, like basically a buffet of talk red flags. I will basically do everything except for read off of my slides, hopefully. The point of this talk really is like there are 3 points to this talk. So the first is, I feel like to some extent, we've been lacking like a clear explanation of what edge compute is actually supposed to be. Second, I want to try to show where it's going in the future. And then third, try to show how we can actually get there. You could also look at this as kind of an intro talk to Chris Micklejohn's talk coming up right after this in the orange tent, is it? Yes. Orange tent, yes. So you should go to that afterward. Right, so I'm Tyler McMullen. I'm the CTO of this company, Fastly.com. I'm also hiring for my team right now, so if you find this kind of thing interesting and you have some experience at it, I would love to chat with you about it. Also, you can argue with me on Twitter here. I love to be told I'm wrong. It's the only way that I learn things. Right, so edge compute is confusing. One of the reasons I want to give this talk is because edge compute has this like kind of weird reputation in that it seems to mean something different to every single person that I talk to. When I was writing this talk, I kept starting and stopping and starting and stopping. And you know, that's weird because despite this being something I have a lot of thoughts and opinions about, I had a really hard time getting started doing it. And I think that part of the reason for this is that it's such a, like, it seems like a vague topic if you're not actually like deeply involved in it. Edge compute is this idea that we should do computations like at the edge, for whatever that means. So I texted a good friend of mine. He's actually like an incredibly experienced developer. He's the like author, maintainer, contributor to software that probably most of us use actually every day. And I asked him what edge compute was, and here's what he said to me. You're an app store for HTTP requests or a shitty middleware? I don't know. So I feel like we might have a marketing problem here, essentially, is what I'm saying. Edge compute is about moving computation close to the source of the data. Like, what do we mean by the source, though? That is also vague. All right. The edge, or the source, has like almost nothing to do with the physical topology of the network. I think that's one of the confusing things. It can be the physical edge of the network, but it doesn't have to be. It's not necessarily about that. What we really mean by this is the source of the input of the system, close to the thing that is generating and potentially also using the data. In other words, the edge is defined by the application, not the physical network. I think this is one of the most misunderstood things about edge compute, ultimately. So what we're referring to as the edge here really does mean something specific, though. It's not quite as vague as it initially sounds. The edge is the endpoint of the application, regardless of where it falls specifically in a physical network. So like what? Right. Well, it can be many things. It's really about, again, where the data is produced and consumed. So for instance, airplanes are a pretty cool example of this. There's lots of computation that happens in airplanes. For instance, takeoff, cruising, landing, the whole autopilot system, right? So it's basically its own little data center. Most airplanes these days have like 3 separate computers that are formally verified and radiation resistant. And like, to imagine like what edge compute is, like maybe imagine what this would be like if we didn't move that computation to the edge. If the plane had to like call back to a central data center to find out whether or not it should like put its wheels down right now, or like what its like specific like yaw and so on should be. Another example, self-driving cars, obvious, right? But even before self-driving cars, like cars had many functions, many computations that they were doing on board, navigation systems and so on, right? Okay, bear with me on this one. The JavaScript we write is also a form of edge compute. Why, right? So edge compute is about, again, moving computation close to the source of the data. So when you validate a user's input, like a form input on a web page, that's exactly what you're doing, right? Instead of doing that at the server, or in addition to doing that at the server, in order to improve latency, in order to possibly improve scalability, you're doing that in the browser. So you're moving that computation to the source of the data, to the place where it's both generated and also used in this case. Again, like client-side sorting and filtering and so on. These are actually, arguably, edge compute. Are you disappointed? I was disappointed when I realized this. The problem is that it's not boring because it's not useful. It's boring because it's obvious. If you generate all the data that you need in order to compute a value in a single place, of course that's the place where you're going to use that you're going to do that computation. Moving it elsewhere would just be wasteful, right? The thing is, we've been doing this kind of edge compute since like basically the dawn of computing for years and years without even like putting a name on it or recognizing it as a thing. So the thing that all these have in common, or not necessarily all of them, but what a lot of these have in common is that they're stateless. In the case of like the browser and validation example, like the edge compute we're describing is entirely stateless. It's stateless kind of in the same way that like a purely functional language is stateless. The validations don't have side effects in this case. The validations, they don't need to query other things and store values in order to make those decisions. It's just a series of functions that are like, is this cool? Yes, this is cool. No, it's not cool. So the same kind of goes for the autopilot and the self-driving car example. Alternatively, there are some examples that are not stateless but are entirely trivially partitionable, which is kind of like a weird thing. So for instance, in the case where you have wow, that's cool. The case where you have a self-driving car that reports back, let's say, aggregates of its own driving stats, right? The car is filled with sensors, which are constantly monitoring the state of things that are going on. With some of those cars, they'll actually build up aggregates of these stats and send them back to some sort of central data store. So in this case, it's not technically stateless. It is actually like building up its own state, but it's only its own state. So it's trivially partitionable. It is just the state that this thing owns, right? Each car, airplane, whatever, are only dealing with their own state. So there must be a good reason for this, right? Like why, if we're doing these computations at the edge, why would we only ever be doing it on stateless or like, things that only have their own state? Well, it comes down to this, edge computing versus coordination, right? There's a tension between moving computation to the edge and coordination. To keep computation centralized, you have if you keep computation centralized, you have all the state available to you. But you also have to get all that state to the centralized system, right? If you move computation to the data producer, you have instant access to it, but you also don't have immediate access to all the other state. So there's this fundamental like headbutting between coordination and edge computing. So for instance, imagine you were, again, designing like a self-driving car. Let's say all the cars on the road are self-driving, and they have like built-in maps of roads, let's say, just as an example. If you want to design this as a centralized system, you could pull all the sensor data into a single place, and you could run algorithms on it. You could do all sorts of things to like optimize, and then you could have all the cars just drive in sync with each other, let's say. It would be like an orchestra conductor, like conducting a symphony of cars on the road. But it's obviously completely unrealistic. Instead, that computation actually has to be done in each individual car, which makes the problem much easier from the perspective that you don't have to move all that data around. But of course, that also makes it harder because you can't actually coordinate between multiple producers and users of that data. The cars don't actually pass data between each other. OK, fine. So I guess edge compute is just useful, but boring. Well, OK. So I guess before I have to walk off the stage in shame and just be like, all right, well, I guess edge compute sucks, let's go back to this notion of coordination. So if edge compute is at odds with coordination, then it's ideally a coordination-free system. What is a coordination-free system, first of all? All right, let's talk about what a coordination-free system isn't, right? So let's say you have a distributed system of some kind, and clients can write some kind of values to it. The specifics don't matter, so let's just say in this case it's unicorns. It's unicorn DB. In this particular case, you want your system to be very consistent, let's say. So you want the servers to agree before allowing a write to happen. And so you send out a broadcast telling the other servers that you want to write a new unicorn. One second. So you get a few responses back, enough to like establish a quorum, let's say. And then only after that do you respond to the user saying, OK, I wrote your unicorn. right? This is kind of like an example of a thing that is not a coordination-free system. You are clearly coordinating between these various actors. So the thing that makes a coordination-free system coordination-free is that nodes must be able to make progress without talking to each other. Actors, nodes, servers, whatever, for a system to be coordination-free. It's easy to see why this is necessary for edge compute applications. If your car needs to get a quorum before deciding to turn, that's going to be like a really bad time for you. So when you think about it this way, it starts to make more sense. It makes sense that the way edge compute is typically done is either with only local data or completely statelessly. Because essentially what we're trying to do is build coordination-free distributed systems. If you have no state, this is easy. If the state is only local, this is easy. But the point is this: coordination-free distributed systems theory should apply to nearly every edge compute problem. That leads me to the realization that what we are in currently is basically the Stone Age of edge compute. And that is where like kind of the exciting bits begin. What we do now is technically edge compute, yes. But even if the current uses of edge compute seem kind of boring and obvious, like we don't need to look for advances in specifically edge compute. We can actually look for advances in coordination-free distributed systems to see where this whole world is going. So let's look at where we can go from here. So there's been like plenty of research in coordination-free systems over the years, but one of the pioneers in the space was research in sensor networks. So sensor networks essentially are just like a large network of sensors that are all trying to like coordinate on determining a particular value or a set of values, essentially. There's like tons of applications for these. Cars and airplanes are like the obvious ones. There's nuclear power plants, there's farms, there's like all the IoT crap that we have now. It's about measuring things and often finding aggregates and running queries over those aggregates. So some of these are like huge, hundreds of thousands of nodes. But if we like look back in time, so this paper is from 2001. And it's describing an in-network processing system, an in-network query processing system for sensor networks. So essentially, it's basically trying to go, all right, I want to do like joins and aggregates over my data, over these like thousands of sensors, right? How can I do that without having to do all the computation in one single place? How can I do that while like utilizing the computation that the sensors themselves have? So the idea is that this is all happening in-network, rather than in a central location, right? So this is kind of like an early example of edge compute in its own weird way, because again, we're moving computation to where the data is produced, where it's like to where it is produced rather than just to where it is consumed. Another example of this, this paper describes the idea that in sensor networks, you often have like partial results or results with error and uncertainty in them, and so we ought to build systems where like wherein the nodes or sensors work together to reduce the errors, to find answers, and to like eliminate uncertainty in the system. This paper was published in 1981. So this like the research on this area like goes back quite a ways. Also, I want to point out the name of the place where this is published, which was the IEEE Transactions on Systems, Man, and Cybernetics, which is like for sure the coolest name of a conference I have ever seen. All right. So moving forward in time, like what about relatively current stuff? Coordination-free distributed systems research. Well, my personal favorite go-to for this kind of work is actually SyncFree. It's a large research project funded by the EU, and they've published some of the most innovative stuff that has come out in coordination-free systems for the last like several years at this point. It's like fantastic stuff. So technically, this is not SyncFree, but like it's from like SyncFree's founder, so it led to a lot of the work they currently do. So what this is the paper that introduced the idea of conflict-free replicated data types, or CRDTs. And I'm going to give an example of a CRDT and how that works. But again, this is like the simplest possible example, and you should go to Chris's talk if you want to know more. So an add-only set is probably the simplest example possible of a CRDT. So the idea with this is that it's a set, but you can't actually delete things from it. You can only add things to it. So how would that work in a coordination-free network? Well, the idea is that the data types, actually no, I will walk through it first. So OK, right. So let's say that we have like 3 separate nodes here, and they're each able to make progress on their own. So let's say like the first one writes 1, last one writes 2. We like replicate the one. We replicate the third node's state to the second node. OK, now it also has 2. All right, now the second node writes 3. And eventually, the idea is that what these do is they form, it's a data type that forms a lattice. Essentially always able to calculate a least upper bound, a join, or a merge, right? So that in this case, it's easy to see that as long as you're only ever adding, you can always merge. You can always union these different data structures together and come up with like the least upper bound of them, the merge, the join of them. There are much more complicated CRDT examples, of course, but they involve essentially passing around causal metadata for deletions and things like this. But so another example of like recent research on this is this the Swift Cloud paper, Write Fast, Read in the Past. This paper describes the design of like a large-scale CRDT-based database. Essentially, it's a database, in this case, for edge compute. Also, we have LASP, again by Chris Michael-John, which is an attempt to develop a language specifically made for coordination-free programming. Even if we know that it's possible to do these things, without the languages, without the frameworks, and without like the metaphors, we're kind of like doomed in this entire idea of edge compute. All right. So one thing that comes through when you're reading all these papers is an interesting fact. The strongest consistency guarantee that you can achieve while not requiring any coordination with other nodes upon writing data is causal consistency. What does that mean? Well, let's say we have 2 actors. We have Jack and we have Jill. All right. So Jack says A. And then Jack tells Jill A. And Jill says, no, 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 B. All right, fair enough. So in this case, we can say A happened before B. We can definitively say that because Jill received the update from Jack of A and then did B, that B happened, or A happened before B, right? Likewise, we can say in this case, after Jill replicates that data back to Jack, that C happened before, or happened after B. However, if Jill then also does D, and they haven't actually coordinated at this point, right? Jill doesn't know that Jack said C. Jack doesn't know that Jill said D. So we can say that B happened before C, and B also happened before D, and C is concurrent with D. This is an example of like causal consistency. Right, so that's like causality, right? But like, what does that get us as far as consistency? What causal consistency gets us is preventing causally impossible states. So let's walk back through this with like real operations and see what I'm talking about. So let's say Jack is inserting X. Jill deletes X. Jill's like, no, 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 not X. Replicates that back, and Jack goes, OK, well, in that case, I will insert Y. And Jill's like, no, I'm sorry, I got this. I'm going to insert Z, right? So in this case, they converge as well. So in this case, we can say that like at the end of the day, like we have Y and we have Z. But the point of causal consistency is preventing those causally impossible states. So we can say that at different points during the execution of this, the set that we're inserting into was either empty, then it was X, then it was empty again, then it was Y, then it was Z, and then it was Y and Z. What it was never is X and Z, or X and Y. Sorry, I know this is kind of dry, but like it's actually kind of an important point. Like the purpose of causal consistency is to prevent those causally impossible states from occurring, to give you some level of consistency that is based on reality. Right. The idea is that like just as in the real world, when we're talking about a distributed system, things can truly happen simultaneously. The time on the wall doesn't really help you when you're building distributed systems. As like, even if you could definitively say that event A happened before an event E based on wall clock time, that doesn't tell you whether A caused B. It doesn't tell you whether A led to B, or whether or not they're like unrelated causally. In order to do that, you need to track the causality and develop strategies for what happens when A happens before B, B happens before A, or when they are concurrent. So why is this so hard? The problem is that like causal consistency is fundamentally at odds with an idea that is prevalent in much of systems development today, and it has been prevalent for years and years. And the problem with this is single system image. So single system image it's an abstraction. It says that a distributed system, regardless of the number of nodes it's running on, should or where they are, should provide an interface that to the outside world appears to be one system, appears to be one single machine, right? The pursuit of this single system image idea is why we have concepts like leaders in distributed systems, and we have things like Paxos and so on. Totally useful in some circumstances, but often over-applied. So another way of describing single system image is to say that the system is linearizable, right? So meaning that to an outside observer, it appears as if every event in the system has an order. It has a total order. So for any two events, you can definitively say that one of them happened before the other. And so everything happens in step, like one foot after another. So once you start running your systems across data centers and regions, and sometimes even in a single data center, you have to grapple with the fact that single system image or serializability or linearizability is not usually realistic to do in practice. It's this relentless pursuit of single system image that leads us to bad, hacky distributed systems design. And so when it comes to edge compute, this idea of single system image doesn't work at all. It's not realistic to hide the fact that your program is running across a network of many machines. And it's, in my opinion, this is the cause of why edge compute and why more complex edge compute ideas haven't really taken off as much as they should yet, because we're all stuck in this idea that there has to be an order, that things can't possibly happen concurrently with each other. And essentially, it's my argument for why we need new concepts, new frameworks, new languages, new metaphors for these things. As I was writing this talk, I was reminded that a friend had written an article specifically about this, entitled "A Certain Tendency of the Database Community," specifically about this particular thing. In retrospect, I should have just put this paper up on the screen and just peeled out. But it was this quote in particular, which I will actually read. "We posit that striving for distributed systems that provide single system image semantics is fundamentally flawed and at odds with how systems operate in the real world." This seems like a really super important point to me, because it is this thing that has caused us to not be able to develop these coordination-free, large-scale, distributed edge applications. That is the missing part. New frameworks, models, concepts, and even languages will be needed to create edge for edge compute to hit the mainstream in a big way. This part of the conversation seems to be mostly missed currently, especially in conversations in industry. I keep seeing edge compute discussed, but it's discussed in a way that goes, well, we just have to move parts of the application out to the edge. It's fine. We'll just move, we'll just do that. We talk about new services. We talk about new products. We talk about applications, but we don't talk about the part that is missing. I mean, even in the IEEE Computer Science magazine last year, this part was discussed as a minor side note, right? On the very last page, after breathless praise of the idea of edge compute, they're finally that. In edge computing, as several research projects have demonstrated, yada, 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 yada. Thus, easy-to-use programming frameworks and tools are required. But the lack of this by itself has the potential to sink the entire idea. So, again, this is why you should go see Chris's talk, because he's working on this. All right, so let's say we could get through this. Let's say we could find a way to address these things. We need to address the fact that many programmers will have a hard time adjusting to this new reality. But let's say we do that. We embrace causal consistency. What does the future hold for us then? So one of the really cool things that I appreciate about the idea of edge compute is that right now, so what I do at Fastly is I run a CDN. And the whole idea of a CDN is to, or at least one of the primary ideas, is to absorb spikes, right? So if 1,000, if 10,000, 100,000 people all want to read one page at the same time on your website or in your API, that you actually only see one request for that, right? And the idea of edge compute, if we can do this well, means that you can absorb write spikes in exactly the same way. If you can develop a system where every node can accept writes and every node can can move forward without having to go back to a central system, it means that you can handle these write spikes in the same way that you can handle read spikes. Essentially, spreading them across many, many servers. Another one, network splits become an annoyance, not a crisis. For so many people right now, like you have a net split in your server and your system, in your data center or across data centers, your system is down. You're having a bad day, ops is woken up, everyone is sad, right? Net splits can cause reads to be stale in an ideal coordination-free system, but it doesn't actually cause failures because, again, it doesn't actually require coordination. And finally, you also get offline operation basically automatically. If you can handle arbitrary network splits, that is essentially the same thing as saying that you can operate offline. What is offline operation if not just a really long network split? And of course, you get like unicorns and rainbows, and we have a long way to go to get there. It appears that I spoke much more quickly than I was expecting to. So in conclusion, okay, what was the point of all this? Despite all my ragging on it, edge compute is actually pretty exciting. The applications we're finding for it today are incredibly useful, but they're really only just scratching the surface. And this talk also is only just scratching the surface of all the research and all the work that needs to go into this. However, to push it beyond the relatively easy applications that we're using right now, we need to look for other forms of research. We need to look back at sensor network research. We need to look at coordination-free distributed systems and others. And we also need those new frameworks, new metaphors, new languages for this. We as programmers are so reliant on our metaphors, essentially, is what I'm saying. Without good ones for edge compute, it's going to be a very rough time. So thanks. Sorry, I know I spoke very quickly there. There are no questions? Seriously? Chris, if you just want to ask, I'll answer. I'll repeat your question. Oh, cool. All right, so first question. What are you running with such... Oh, uh-oh. OK. What? I'm going to start at the... God. All right. What are you running with such paradigms at Fastly? This is a great question. So CDNs at their core are, in fact, in many ways a coordination-free distributed system. They are, in fact, a primitive form of edge compute. At Fastly, we are... we actually allow people to do some level of computation at the edge using varnish configuration language, which is a reasonable language for doing this kind of thing, for filtering queries, for modifying responses, and so on. But ultimately, it's kind of the same thing that I was saying, where we are only dealing with local data. We're only dealing with stateless computations, right? So we will see where Fastly goes with this in the future. I will say that we are working on it, but yeah. So what current metaphors for edge compute are decent? This is also a really good question. I think a lot of them come down to that causal consistency. It comes down to viewing consistency in the same way that the real world happens. If you're trying to make, let's say, plans with a group of people, this is one of the classic metaphors for causal consistency. If you're trying to make plans with a whole group of people and you don't have some sort of atomic way of communicating between all of them, you're not all on the phone together, then you're going to have the same level of causal consistency problems. You're essentially doing the same sort of thing where you have three people who are communicating, and one of them says, OK, let's meet at this time. So these two people think this time, and the third person says this time, but only one person says. So essentially, you end up with exactly the same problem with that. As for other metaphors for it, yes, of course. A lot of the ideas that go into CRDTs at this point and also causally consistent transaction systems, which you should totally read the papers on, are actually getting there for this as well. All right. I'm going to skip down to the bottom one and say, causal consistency is sufficient for a lot, but some invariants, non-negative balance, require coordination. How can you handle right spikes for these operations? I wonder who wrote that one. The answer is, I don't actually know. I don't know the answer to this. I'm not sure if you can. But I would love to find out if whoever asked that question would like to explain it to me. So, all right, I'm going to call it good for now. Thank you very much.